This video is for Lesson 7-8, Applications of Quadratic Equations. We'll do a couple example problems. One base of a trapezoid measures 5 centimeters more than another. The altitude is 4/5 as long as the longer base. Find the lengths of the bases if the area is 100 square centimeters. This question refers to a trapezoid, which is a shape you'll study in geometry class. Let's draw one over here on the side. The trapezoid has one pair of parallel sides. So the way I've drawn this, I've made it the top and bottom sides, which are the ones that are parallel. We're told that one of the bases is 5 centimeters more than the other. So let's label the top x because we don't know how long it is, and label the other base x plus 5. That takes care of the first sentence we were given. We're told the altitude is 4/5 as long as the longer base. So in our trapezoid, the side that runs up and down is 4/5 of the x plus 5. So I've labeled that on this side of the trapezoid. And that takes care of the second sentence of information. Now we're asked, find the lengths of the bases if the area is 100. So in geometry, you'll learn the area formula for a trapezoid. 1/2 times the height times the sum of the bases. We'll call the top base base 1 and the bottom base base 2. Now let's make some substitutions. For area, fill in 100. For the height, fill in the 4/5 x plus 5. For B1, fill in x, and for B2, fill in x plus 5. You notice this creates an equation that has only the variable x. So let's do some simplifying on the equation. 1/2 times 4/5 is 2/5, which gets multiplied to that x, creating 2/5 x, and would get multiplied to the 5, creating a positive 2. Because 2/5 times 5 would make 2 when the 5's cancel. That's what this part simplifies to. Now let's work in this set of parentheses. This makes 2x plus 5. Next up, let's do FOIL on the right side. 2/5 x times 2x makes 4/5 x squared. Now the outer product, 2/5 x times to the 5, makes positive 2x. Now the inner product, 2 times 2x makes 4x. And now last, 2 times 5 makes 10. Let's remove the fraction by multiplying everything by 5. So we have 500 equals 4x squared plus 30x plus 50. I got 30x by combining 2x plus 4x, which is 6x, and remember, we were multiplying by 5. Next up, let's create standard form by subtracting the 500 to get a 0 on one side. We have 4x squared plus 30x minus 450 is equal to 0. We can use this as our standard form, where this is A, this is B, and this is C, and use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Let's make our substitutions. Negative b becomes negative 30. b squared becomes 900. The letter a is 4. And the letter C is negative 450. And that's all divided by 2 times A, which would make an 8. Next up, let's simplify in that radical. This makes the square root of 8,100. Next up, this makes negative 30 plus or minus 90 all over 8. This is going to lead to two answers. First, let's go negative 30 plus 90, which is 60, and go 60 divided by 8. We get 7.5. For the other answer, go negative 30 minus 90, which is negative 120, and divide by 8. And that makes negative 15. Now think about what the letter X is representing. It is the length of the top base. Can a length be a negative number? That doesn't make any sense, so cross that one out. We have figured out that the top of the trapezoid is 7.5 centimeters long, and the bottom of the trapezoid is 5 more than that, so that's 12.5 centimeters long. Here's our second example. Because of car trouble on the return leg of a 180-mile round trip that took 5 hours, Shayla's average speed coming home was 15 miles per hour less than her average speed going. If she'd been able to maintain the same speed coming home as going, what would her total driving time have been? This question involves distances, rates, and times, so the formula D equals RT will become helpful. This formula can be solved for either letter R or T as well. For example, T is equal to D over R. Let's work with how much time Shayla takes to drive to her destination. I'm going to write that as time going. And the other thing will be her time returning from her destination to home. Let's try to model these with algebra expressions. The time it takes Shayla to go to her destination will represent with the variable t and a little 1 by it. That will be equal to the distance of 90 miles divided by her rate of speed. We don't know her rate of speed. Let's use the letter R to represent that. The reason I've used a subscript of 1 is because there's going to be a different time involved on the return trip. So we'll call that T2. Her return trip is also 90 miles, but her rate of speed is 15 miles per hour less. So that's R minus 15. This equation represents the time going to the destination. The second equation represents the time returning. In the first sentence, we're told that the total time is 5 hours. So let's add together the time going plus the time returning. We know that that is equal to 5. Let's substitute our expressions in there that have the letter R in them. So 90 over R plus 90 over R minus 15 is equal to 5. At this point, we recognize an equation of the type that we've solved this year. It has fractions. We need to times by the lowest common denominator. So in the first one, we will times by R times R minus 15. The same for the second fraction. And the same over here. By doing that, the r's cancel away here, leaving 90 times r minus 15, plus, and here in the middle, the r minus 15's cancel, leaving 90r, and that's equal to 5r times r minus 15. Let's do some distributive property. We have 90r minus 1,350 plus 90r is equal to 5r squared minus 75r. This is going to be a quadratic equation because of the highest degree of 2. Let's keep going on the simplifying. We have our 5r squared, then negative 255r, then plus 1,350. That's equal to 0. What I've done is try to create standard form by getting a 0 on one of the sides. I left the 5r squared where it was, and I subtracted the two 90r's away from the negative 75r. That got negative 255r. And then I added the 1350 to get it on the same side as the 5r squared. That made a 0 on the left side. And then with the symmetric property, I just flipped everything around. Now before doing the quadratic formula, we can make this a little easier because everything seems like it divides by 5. So we have r squared minus 51r plus 270 is equal to 0. Let's solve this quadratic equation with any of the methods we know. It's possible it could factor, but I don't want to mess around with different combinations that make 270 and maybe add up to negative 51. Let's just go directly to using the quadratic formula. Negative b will be 51. B squared will be whatever negative 51 squared makes. That's 2,601. Then minus 4 times 1 times 270. And that's all over 2 times 1, which is just a 2. Next step, let's simplify in the radical. We end up getting 1,521 in there. And that's still all over 2. This is going to make 2 answers. Let's use a calculator and go 51 plus that square root and then divide by 2. R turns out to be 45. Remember, that's the speed, so miles per hour. Let's type it in again, but this time use the subtraction sign. I typed 51 minus the square root of 1521 and then pressed enter before pressing divide by 2. This turns out to be 6. Now let's check and see if both of these are possible speeds. A speed of 45 miles per hour sounds very realistic for driving a car down a road. A speed of 6 seems really small, and I also noticed that if r was 6, that 6 minus 15 would make a negative number, which you can't have for a speed. So it doesn't make any sense to use the answer of 6. Let's use the answer of 45. Do you remember what the question was? What would her total driving time had been if she could have the same average speed coming home as going? So let's focus on the equation that we wrote about the time going. If r is 45, if you plug a 45 for r, what does that time turn out to be? It turns out to be 2 hours. If she could have the same time returning, that would also make 2 hours. And so her total driving time would have been 4 hours. In this lesson, we did 2 application problems together. We used formulas from geometry class and from physics class, which then created algebra equations that involve quadratics. At that point, we were able to use the quadratic formula to solve our problems.